This lesson is on a topic called impulse and how that relates to what we already know about momentum. So remember from our last lesson that momentum is an object's mass multiplied by its velocity. P equals mv is the formula we learned. What I want to start by doing in today's lesson is looking at Newton's second law and showing you that Newton's second law can actually tell us something interesting about momentum. Even though momentum doesn't appear in Newton's second law, there's some key information about it sort of hidden in there. So as a reminder, Newton's second law is this. In other words, the sum of all forces is equal to an object's mass times its acceleration, or sigma f equals ma. Now I'm just going to rewrite this, but I'm going to write my a, my acceleration, in a slightly different way. So what I've done here is I've used the fact that acceleration is defined as the change in velocity divided by the change in time. And I've just rewritten the formula by substituting that in. Next step, I'm going to take this delta t, and just to clean things up a bit and kind of get rid of this fraction over here, I'm going to take that delta t and I'm going to move it to the other side of the equation by multiplying both sides by it. That gives me this. Now, again, like I said, momentum doesn't appear explicitly in Newton's second law anywhere, but there is something at this point that's starting to look a lot like momentum. Remember, momentum's mass times velocity, and here we have mass times change in velocity. So although that isn't exactly momentum, it's pretty close. What that is change in momentum. So this tells us, by just taking Newton's second law, substituting some stuff in, rearranging it, it tells us that the net force on an object multiplied by the amount of time the force acts is equal to the change in momentum of the object. So that's an important enough equation that we're going to write it down in this box here. Okay, and then I'll also just remind us that this first part, the sigma f, is the net force on an object. This part here, the delta t, is the time the force is applied for. And then delta p, or delta rho, is our change in momentum. Now, this is an important enough equation that we actually have a specific name just for the left-hand side here. That whole side of the equation, the sigma f times the delta t, is called impulse. And looking at it, you can probably guess the units of impulse. Since it's a force times a time, that means the unit should be newtons times seconds, or Newton seconds. Now, remember that a Newton second, the unit of impulse, is actually mathematically equivalent to a kilogram meter per second, which is the unit for momentum. that we talked about. So it actually doesn't really matter whether you use units of Newton seconds or of kilogram meters per second, because they're exactly the same thing. Convention, however, is that when we're talking about momentum, we use kilogram meters per second. And when we're talking about impulse, we use Newton seconds. However, this formula over here tells us that impulse is equal to momentum, or the change in momentum. So it's really not that important which one we're talking about, since they're effectively the same thing. So the important thing that this equation tells us is that to change the momentum of something, you have to give it an impulse. If you want to change something's momentum, you need a net force on it, and you have to apply that force for a certain amount of time. Without those two things, you can't have an impulse, and without an impulse, you can't change an object's momentum. So let's look at an example here. We've got Luigi, sick of taking orders from Mario. So he takes matters into his own hands. He swings a 9-kilogram hammer at 16 meters per second right at Mario's face. As the hammer strikes Mario's face, however, Mario's cushy mustache, kind of like a big pillow in front of his face, brings the hammer to a stop over a period of time of 1/4 second. We want to know, what is the force exerted on Mario's mustache by the hammer? So I'll do my best to draw a little bit of a diagram for you here. I think Mario's the red one. So let's start with red. There's Mario, and here's his cushy mustache. Luigi has swung a hammer, and it's just come in contact with Mario's mustache. Now, over a period of time, 0.25 seconds, the mustache compresses and it slowly brings the hammer to a stop. So we'll redraw what this scenario looks like 0.25 seconds later.
Mario's a little scared now. And his mustache is a little more compressed.
So let's then see what our new formula, the principle of impulse and momentum, can tell us about this problem. So let's plug in some things we know. I think we know what delta T is. That's my 0.25 seconds. That's how long the force acts for. And we know that the change in anything is final minus initial. Plugging in a few more things that we know. Momentum is mass times velocity. And then I think we know the mass of the hammer, and we know the initial velocity of the hammer and the final velocity of the hammer. So we can plug in numbers in for all of those things. And remember here, since velocity is a vector, that's why I've got this important vector hat up here. Every time I put in a number for it, I have to be very conscious of its direction. In a case like this, that means I have to think, is this number going to be positive or negative? So in this question, I've just kind of decided that the way I've drawn it in the diagram, I'm going to pick to the right to be positive and to the left to be negative. So since the hammer is going to the right to start with, that means initial velocity will be a positive number. Now, if I do this math here, and then I divide by 0.25 to give me sigma f all by itself, I get sigma f equals negative 576, or 576 newtons left. So let's recall what we were being asked here. The question asked us to find the force exerted on Mario's mustache. And we got an answer that said left. Looking at my diagram, that doesn't seem quite right. I would think Mario's mustache is feeling a force to the right from this collision with this hammer. So what's going on here? Well, in the principle of impulse and momentum, which we started with up here, it talks about an object whose momentum is changing and how that object has to feel a force for a period of time. The object whose momentum is changing is not the mustache, it's the hammer. The hammer is the thing that feels the change in momentum. So what this formula tells us about is the net force on the hammer and the amount of time that force acts for. So what we've actually found is that the force on the hammer is 576 newtons left. So how can we use that to figure out what the force on the mustache is? Well, you might recall that Newton's third law tells us every action has an equal and opposite reaction. So what that means when we apply it here is that if the mustache pushes on the hammer with 576 newtons left, then the hammer has to push on the mustache with 576 newtons to the right. Okay, last thing I want to talk about is an application of the principle of impulse and momentum to sports. Well, to a variety of things, but one of them is sports. And I want to talk about this idea of following through when you're playing a sport. There's lots of sports where we talk about this. If you're kicking a soccer ball, we can talk about following through. If you're hitting a baseball, we talk about following through. Hitting a golf ball, we talk about following through. And the principle of impulse and momentum kind of sheds some light on why that might be important. Let's start by writing the principle out again for ourselves down here. So let's take, for example, the golf scenario. You are trying to hit a golf ball. Say it's your first hit, and you're driving the ball and you basically want to hit it as far as possible. You want to get that ball going as fast as possible. You want to give it a big change in momentum. Its momentum is currently 0. You want to give it as much momentum as you can. So big change. In order to do that, there are 2 things the ball needs. It needs a net force, and that force has to act over a period of time. Now, obviously, you're going to hit the ball with as much force as you can. That part's pretty intuitive. But let's assume you've hit the gym. Let's assume you've kind of worked on your stroke and on your technique enough that you can get that force to be as big as you possibly can, and you're hitting the ball with maximum force every time. The other thing you have some control over is how long that force is applied for. Let's look at a picture of a golf swing here. So here's a golfer lining up for a swing, and you can see kind of the shots of this swing going from left to the right. The moment where he makes contact with the ball is right here. He has hit the ball with a certain amount of force, and now he kind of has an option. He could basically stop swinging and stop his club in this position right where it is in the middle of the photo. After all, he's already made contact with the ball, right? If he stops his swing right there, the ball should move. However, what he does is he continues to follow through. He continues his swing throughout the rest of the picture. Now, there's a few reasons why golfers will do this. One of them is that, and you'll realize this if you watch sort of slow motion videos of golf drives, even after you first contacted the ball, the club generally stays in contact with the ball for a portion of the swing. It's not just in contact with the ball for an instant, it's in contact with the ball for a period of time, and they move together before the ball actually leaves the club and flies off the screen. So by following through, you are making sure that your club is in contact with the ball for as much time as possible. So by thus increasing this delta T, and that gives you the biggest possible change in momentum for your ball, giving you a nice long drive. So this also has to do with why cars have crumple zones and why people tend to bend their knees when they jump and land on the ground. Both of those things, the crumple zone and the bending of your knees, are designed to increase the amount of time that a force is applied to achieve sort of either a greater change in momentum or to achieve the same change in momentum, but while requiring less force. That's all for the lesson today. We'll see you at the next lesson where we talk about conservation of momentum.